My name is Hitong Lee. I'm going to make a presentation about research on Tetris algorithm design. First of all, I would like to go through the outline of my presentation. As the slide shows, I will talk about why I picked Tetris as the topic of my research project. Then I will show some past works that were active in recent years. This may give a better idea about the reason why Tetris is still interesting to me. After that, I will focus on my algorithm design experience, which is the main part of the presentation. Since my algorithm is certainly not perfect, I will talk about possible improvements and optimizations that I thought about but did not have enough time to realize. You might ask why I picked up an old and simple game, Tetris. In fact, yes, Tetris is one of the classic board games which was created in July 1984 by a computer engineer in Russia. After it was created for 4 years, people start thinking about whether Tetris can be played forever. It first encountered in a thesis by the author of the book, Can You Win at Tetris? From that point, people found that Tetris is actually not as simple as it looks. It has several complex mathematics models behind it. Moreover, it's already been proved to be NP-complete problem in 2002. As the algorithmic theory of games becomes more and more active, Tetris is brought back to academic area. In addition to that, some researchers in artificial intelligence also view Tetris as a great game for reinforcement learning. Now I will briefly talk about some existing work on Tetris in recent years. Tetris is starting in various directions. I will only focus on the past work in two areas I mentioned earlier, algorithmic theory of games and AI. The area of algorithm theory of games, I listed two papers that prove playing offline Tetris optimally is an NP-complete problem, where offline Tetris means the initial board and piece sequence are known beforehand. The first is Tetris is hard even to approximate. It proves that the offline version of Tetris is NP-complete to maximize the number of cleared rows, or to minimize the maximum height of an occupied square, or maximize the number of pieces placed before the game ends. It furthermore shows that the extremely inapproximability of the first and last of these objectives. The second paper is an extension of the previous paper. They also prove that Tetris is NP-hard, but they use a less complex sequence of Tetris pieces and did not put limitation on the three-partition problem as the previous one did. In artificial intelligence area, Tetris is also widely used for reinforcement learning. Here I listed two papers involving Tetris in AI area. They are from the same author who tried to apply reinforcement learning to Tetris. He also listed some mathematical model and past implementations of Tetris games used in AI in his paper. As to my project, the target of my project is to design and implement an algorithm for Tetris that can eliminate as many lines as possible. From the paper I referred just now, Tetris is NP-hard and NP-complete. As for now, an optimal solution is not possible. So I was interested in how well my algorithm could do. As to implementation, I used the example program in C++ from Qt website as the base program and added in the implementation of my algorithm. And the board size using Qt example is of 30 squares high and 15 squares wide. The global procedure of my algorithm is pretty simple. First of all, for the current piece, all possible placement and rotations are generated for further consideration. Then I will go through all the possibilities and give each an evaluation score based on a defined evaluation function. At last, place the current piece to the placement with the highest evaluation score. So I only made in-time decision, but not consider one or more step look ahead. Every decision made is only based on the current board status and the current piece. Before I go deep into the algorithm design process, I want to clarify some terms I use in the algorithm description first. In my algorithm, by piece, I mean the tetraminos. As the picture showed here, to differentiate shapes, I will call them I, J, L, O, S, T, Z, as shown in this graph. And by blocks, I mean the squares that compose the pieces, like this. Obviously, in the standard Tetris, every piece is composed of 4 blocks. By holes, I mean blank squares that are blocked by surrounding pieces, like this picture shows here. And by deep holes, I mean the sequence of holes together but reachable from the top. This is special because this kind of shape depends on the eyepiece too much, like this picture shows. With those terms in mind, now I will go detail about my algorithm design process. My first idea is pretty simple. Based on experiences of playing Tetris, I consider 3 situations. First, it's obvious that eliminating lines is a superior choice. If I'm not able to eliminate a line, I will try to make the board pile as low as possible. In the meanwhile, I don't want to create too many unreachable holes, since holes are very hard to eliminate. With those considerations, I have my first evaluation function. As I showed here, score equals to lambda 1 times removed lines, minus lambda 2 times average height, minus lambda 3 times number of holes, where lambda 1, lambda 2, and lambda 3 are all greater than 0. After implementation, I was able to eliminate around hundreds of lines, but this is too far away from a good algorithm. From observation, many wrong decisions were made, so I started to seek improvements. Since the first algorithm, I scanned the placement from left to right and calculated the average height of the board, so it often happened that the left side was very high while the right side was very low or even empty. Thus, I decided to calculate variance in addition to calculating the average height. Other than that, I thought the coefficients before 3 consideration terms would affect the performance a lot, since coefficient value determined the level of a consideration was emphasized. The pile on the board was more balanced this time, but it also increased the possibility of creating holes. However, as a result, no significant improvements was achieved overall. It was still only able to eliminate hundreds of lines and seemed that coefficient did not affect the performance that much. Then I somehow got stuck on the next improvement.